Have you ever wondered what makes up everything around us? Tiny particles, too small to see, operating under completely insane rules that defy every intuition we have about the world? Welcome to quantum mechanics, the field of science where reality is rewritten in the most spectacular way. This isn't just a story about physics, it's an adventure into a surreal universe where what you thought was impossible is actually self-evident. Let's explore the marvelous world of particles and strings, where ambiguity and uncertainty are the foundations of everything. We'll dive deep into mysteries that completely change how we understand the universe, from the smallest atoms to the most complex interactions. Prepare for all your preconceived notions about reality to be shaken, because quantum mechanics will lead you to the boundaries of knowledge, where science meets magic. Get ready for an unimaginable intellectual journey that goes far beyond the limits of classical thinking. The quantum world awaits your discovery. Welcome to SpaceTime's journey of cosmic exploration, where we uncover the universe's deepest mysteries. In this video, we'll explore the topic, quantum mechanics, the surreal world of particles and strings. Don't forget to subscribe to the channel so you don't miss other exciting videos exploring the universe. If you find this video interesting and useful, please like and share to support us. Quantum mechanics is not just a theory, but a broad theoretical framework describing the behavior of matter and energy at atomic and subatomic levels. It emerged in the early 20th century when scientists realized that classical physics couldn't explain many observed phenomena at very small scales, such as blackbody radiation or the photoelectric effect. Max Planck, with his idea of energy quanta, paved the way for this revolution, proposing that energy cannot be emitted or absorbed continuously, but in discrete packets. One of the most fundamental and shocking concepts in quantum mechanics is wave-particle duality. According to this, tiny matter particles like electrons and photons not only possess particle properties, but also exhibit wave-like characteristics. They can behave as individual objects at one moment, but then spread out as a probability wave through space, creating a complex and contradictory picture for conventional thinking. The famous double-slit experiment is the clearest demonstration of wave-particle duality. When electrons are fired through two slits, they create an interference pattern on the screen behind, just like water waves. However, if we try to observe which slit the electron passes through, the interference pattern disappears and the electrons behave as individual particles again. This highlights the peculiar role of the observer in the quantum world, an idea that Einstein found very difficult to accept, leading to his famous quote, "God does not play dice." Heisenberg's uncertainty principle is another pillar of quantum mechanics, asserting that we cannot simultaneously determine both the precise position and momentum of a particle. The more accurately we measure a particle's position, the more uncertain its momentum becomes, and vice versa. This is not due to limitations of measurement equipment, but rather an intrinsic property of the universe at the quantum level, an inherent ambiguity that cannot be overcome. Quantum superposition is another phenomenon that makes the quantum world surreal. A quantum particle can exist in multiple different states simultaneously until it is measured or observed. A famous example is Schrödinger's cat, which is both alive and dead at the same time in a box until we open it to check. This illustrates the indeterminacy of reality before the intervention of an observer. This phenomenon has enormous potential applications in the field of quantum computing. Instead of using traditional bits that can only be in a state of 0 or 1, quantum computers use qubits that can exist in a state of 0, 1, or both simultaneously. This allows quantum computers to perform parallel computations on multiple states, opening up the ability to solve complex problems that classical computers cannot, such as designing new materials, drug discovery, or cryptographic decryption.
Quantum entanglement. also known as spooky action at a distance, as Einstein called it, is a phenomenon where two or more quantum particles become mysteriously linked. No matter how far apart they are, the state of one particle will instantaneously affect the state of the other. If you measure the state of one particle, you will instantly know the state of the other, without any time for signal transmission. This violates Einstein's principle of the speed of light, but has been proven through numerous experiments. Quantum entanglement plays a crucial role in quantum cryptography, enabling the creation of completely secure communication channels. Any interference or eavesdropping during communication will alter the quantum state of the particles, immediately alerting users to the threat. This creates a security system that cannot be broken by classical computational methods, offering hope for absolutely secure information systems in the future. The Standard Model of particle physics is a brilliantly successful theory that synthesizes quantum mechanics and special relativity, describing three of the four fundamental forces of nature: strong, weak, electromagnetic, and all known fundamental particles. This model classifies particles into fermions, matter, and bosons, force-carrying particles. However, it has not yet been able to unify with gravity, which remains one of the greatest challenges in modern physics. Many unanswered mysteries still persist in quantum mechanics. The nature of consciousness and its role in wave function collapse, or the unification of quantum mechanics with Einstein's general relativity to create a unified quantum gravity theory, remain major questions. Scientists are striving to find a theory of everything that can explain all forces and particles in the universe, thereby providing a comprehensive understanding of reality. Quantum mechanics has completely changed how we perceive the universe. It is not just a collection of complex formulas, but a lens that allows us to look into the deepest depths of reality, where anything is possible and nothing is certain. From explaining atomic structure to developing laser technology, semiconductors, and soon quantum computing, its discoveries have shaped the modern world and opened new doors for the future. The success of quantum mechanics lies in its ability to accurately predict experimental results with astonishing precision. Although its concepts often defy intuition, its mathematical predictions have been proven repeatedly. This reinforces its position as one of the most powerful and most successful scientific theories of all time. Every day, we continue to explore new facets of the quantum world, expanding our understanding of how the universe operates. Scientists worldwide are working tirelessly to decipher the remaining layers of mystery, pushing the boundaries of human knowledge and shaping a promising future with groundbreaking technologies. For example, the development of ultra-sensitive quantum sensors could revolutionize medicine, allowing for disease diagnosis at the earliest stages. This technology can detect subtle changes in the body that current devices cannot. Or, in global positioning, ultra-precise quantum clocks could enhance accuracy by thousands of times, providing nearly perfect navigation capabilities. These applications are just a small fraction of the myriad potentials that quantum mechanics promises to bring to our lives. Furthermore, research into quantum materials is leading to the creation of metamaterials with unprecedented properties that could revolutionize the energy, electronics, and aerospace industries. From room temperature superconductors to materials capable of more efficient information storage, the quantum world is opening a new era of engineering. Deep insights into quantum interactions are also helping us better understand the origin of the universe and fundamental physical constants. Questions like, why does the universe exist? Or what happened before the Big Bang? Might find answers in quantum theories of gravity.
Although still debated and without final answers, quantum mechanics provides a robust framework for asking the deepest questions and seeking groundbreaking explanations. It challenges us to expand our imagination and accept that reality can be far more complex and diverse than we once thought. This quest is a continuous journey, reshaping human knowledge and giving us a deeper insight into our place in the vast cosmos. Each new discovery in quantum mechanics opens a new horizon, bringing us closer to deciphering the universe's greatest mysteries. Although quantum mechanics has unveiled profound mysteries of the universe, it is still not the complete picture. The biggest challenge is how to reconcile quantum mechanics with Einstein's theory of general relativity, especially when it comes to gravity and singularities like black holes or the Big Bang. This is where string theory comes in, a bold attempt to create a single theory of everything that can explain all fundamental forces in particles. In our next video, we will explore string theory, delving into whether these tiny, vibrating energy strings truly hold the ultimate answer to physics's biggest questions. Don't miss this dramatic journey, where we will transcend the limits of space-time to seek answers to the greatest mysteries of the universe.